Broadcast is now starting. All attendees are in listen-only mode.
Uh-oh, we just hit the wrong button, guys.
What?
Somehow it went into broadcast mode.
Oh,
Hello, everyone. Thank you for joining us for today's session, 20% Stretch Code Provisions, a new energy standard for cities and states. I am Connie Chris, Communications Manager at New Buildings Institute. Before we begin, I have a couple of housekeeping things to tell you about. First, you are muted and we cannot hear you. This helps keep the background noise down so that everyone can better hear the speakers. I want to direct you to the dashboard that you should be able to see on the right-hand side of your screen. If you are having technical difficulties and cannot see the slides or hear our speakers, you can use the question pane in this dashboard to let us know and we will help you as we go. We will take questions at the end of the webinar, but you can ask questions anytime during the session using that same question pane. Presenting today are NBI Technical Director Mark Frankel and Project Manager Mark Lyles. Mark Frankel is a leading advocate and technical expert in commercial building performance, setting the vision for what's next in building design practices and leading on market adoption strategies. Mark Lyles provides technical and design expertise, project management, and research support on programs related to zero net energy buildings, new construction, and commercial real estate. I will pass it over to Mark.
thanks, Connie, and welcome to our webinar. Thank you so much for joining us to discuss our new model stretch code provisions that we have just recently released. To give you an idea of what we're going to do today, we're going to first, I'll tell you a little bit about the background of why we undertook this project. We'll talk briefly about what a stretch code is and how they're adopted. We'll go through a savings overview for the package we're presenting. We'll talk specifically about what's in the package, and then we'll take a little bit of time to go through some of the commercial measure descriptions and the residential requirements in this package. Then we'll wrap up with some discussions about where codes are going next, in our opinion, and how we want to continue to support that, and then we'll take your questions. To start, I want to tell you a little bit about the background of this project. This project was conceived out of a project we're working on with Architecture 2030 and Resource Media and the Urban Sustainable Directors Network, USDN, called the Zero Cities Project. We also have some new participants in that project working on social equity as well. But when we started this project, it was a focus on 12 cities in the US that had set aggressive climate goals to meet their Paris Accord commitments. And one of the key desires of that group was to have the ability to move forward with codes at a more rapid pace. With that in mind, Ed Masria put together a coalition that sent a letter to the Department of Energy requesting support for a REACH code strategy, and DOE generously provided support to PNNL to provide analysis of this project of the savings so that we could be sure of our outcomes. The technical development of the REACH code was supported by the Energy Foundation. So as you know, there's been wide adoption of aggressive code and performance goals in the US. The 2030 Challenge, released by Architecture 2030 almost 10 years ago now, was signed on to by ASHRAE, the USGBC, the US Conference of Mayors, a bunch of states and other organizations, and GSA, widely adopted commitments to building performance improvement to support climate goals. The 2030 commitment by the AIA also supports this as well, and California Big Bold Goals, etc. Interestingly, since the Paris Accord, a whole bunch of cities and states have also signed on to meet the Paris Accord. Even though the US pulled out, the cities and states decided they were going to proceed with their commitment to the Paris Accord goals. And now 372 cities in North America have greenhouse gas reduction goals. So there's wide precedent and goals for improvements in building performance. That led us to adopt a series of goals for model stretch code strategies. The first is a 20% improvement over 90.1 2013, which we set as the baseline in this case. That is what we'll be talking about today. We're working on a 40% improvement over that standard and a ZNE code strategy as well. You see on the slide here that we talk about the 20% improvement as a stretch code and the 40% improvement as a design standard. This is because it becomes more difficult to achieve that level of savings within the code process. It's not impossible, and we're working on it, but there are many aspects of building performance that are outside the scope of code and need to be addressed perhaps by design standards or other policy measures. For example, plug loads, unregulated loads, process loads, cooking loads, things like that are not really regulated by energy codes. And so to achieve the kind of performance improvement we need in those areas, we might be talking about other mechanisms than code. But of course, we're trying our best to get as much into code as we can. So some terminology, just for background here. We talk about this as a series of measures for a stretch code. Other people call this a reach code or a step code. There are some places on the continent where these things mean different things. There are places where the uses are interchangeable. For the purposes of our discussion, we consider them all to be a similar process, which is the idea that you adopt a set of code measures that predict what's going to be base code next. That is, you adopt a set of measures that allows people to understand what's coming down the line for the next code cycle. So industry and designers and policymakers and code officials can be prepared specifically for the measures that are already planned. The difference between that and the conventional code process is it gives you some planning horizon, and you set specific targets for future codes so that everyone understands where we're going with code, instead of it being a horse trading session at every single adoption cycle. Also, keep in mind that what we're talking about here is a set of code provisions or measures. We've developed a series of technical strategies that increase the stringency of codes. They can be adopted on top of other codes, but we have not written a complete alternative code. So you have to use our code strategies in conjunction with an existing code in force in your jurisdiction. So when we talk about codes at NBI, we tend to give a score to codes so that we can understand how stringent they are relative to a baseline. This is the chart we use to talk about this. We use what we call the Zero Energy Performance Index. And you can see on the bottom trajectory, the 45-degree line sloping down here, that codes have increased in stringency over time from the starting point. The original 2030 challenge was based on the turn of the millennium building performance, which was represented by the Commercial Building Energy Consumption Survey, or CBEX, released in 2003. We set that at 100, and we track performance of buildings and codes relative to that starting point over time. So on the lower bar in this graph, you can see how we score energy codes. This is based, whenever possible, on determination analysis that DOE conducts on energy codes, where they, every so often, every time a new code cycle comes out, they identify how much more stringent the code is than the last time. And we convert that into our ZEPI scale here. 90.1 2004, the ASHRAE code standard from that year, has a score of 75 on this scale, and we continue down the trajectory, as you can see. This model reach code that we're talking about today, if adopted over another code, we anticipate has a score on the ZEPI scale of 42, which you can see is well in line with the trajectory set by the 2030 challenge. The upper trajectory you can see shows what the commitment that cities and states and governments have made for the Paris Accord. This is what the improvement in existing building stock would look like over time if we meet our Paris Accord goals for an 80% reduction in carbon by 2050. You can see that 90 up here for CBEX 2013, that although there has been some improvement in existing building stock, we have a long way to go to bring that down to alignment with our goals. So we're in good shape on the new construction codes, and that's what we're going to talk about today. So as many of you are aware, adoption of energy codes is a state prerogative. So it happens on a state by state level. The state decides what their policy in their state is for the energy code. But different states have different code stringencies, for one thing, and for another, some states allow cities within the state to adopt energy codes on their own. So the state policy is to allow cities to decide what energy code to enforce. This map is from BCAP, the Building Codes Assistance Project. It shows the relative stringency of different states and shows which states have no specific policy on code. And this is the kind of information you need to understand who can adopt a REACH code. In some places, the state has to adopt any any code policy whatsoever. In other places, individual cities have the ability to adopt their own code. So this becomes important when we start talking about cities wanting to adopt REACH codes. First, they have to be authorized by their state to do so. There are other ways to influence building performance besides energy codes. Although energy codes tend to be the most consistent and strongest that we know of, there are other ways to approach policy on buildings with zoning incentives, permitting incentives, utility incentives, taxes, fee bates, utility rates, annual review of building performance, influence on the market, or encouragement of market adoption. There's a whole host of tools available to cities and states to influence building performance. Codes and stretch codes are a very important part of that, but not the only thing. So let's talk about the savings that we're anticipating with the measures we have adopted here. Again, as I mentioned, this is from an analysis by PNNL that they conducted in conjunction with us building these measures out. We're also working with PNNL on another of other state and city REACH codes in New York and elsewhere. So we've got a great relationship with them and have we're really pleased to have worked with them on this analysis. So remember that this was originally intended to be a code for city adoption. So we focused on denser, larger building types more associated with most cities. The savings apply to other building types as well, but we focused our analysis on larger buildings, as you might see in cities. And we had 5 building types in this analysis across 6 climate zones. The building types we focused on were large office, large hotel, high-rise apartment, standalone retail, and secondary school, which covers a pretty broad swath of the market in the analysis. The analysis that we built for this is available from our website. There's a bunch of documentation that I'll talk about in a few minutes, but I want to show you the way we look at savings in this case. This is the example of a large hotel in climate zone 3A. The outer part of this graph shows the end use breakdown of a building that meets the ASHRAE 90.1 2013 standard. And the inner ring shows the end use breakdown of a building that meets the enhanced requirements after these stretch code strategies are adopted over that standard. So what you see is you can see where the end use savings for this particular building type are from these measures. In the case of large hotel, we get a significant amount of savings in the service hot water area and another significant amount out of heating. That's a 55% reduction on heating from the heating energy, not a 55% reduction in building energy, of course. But you can see how the end use breakdown of savings came out in this analysis for large hotel. And for comparison, here it is for a secondary school in climate zone 4C. And again, you can see the individual breakdown of savings. In this case, our largest category was in interior lighting, but we also got significant savings in heating and service hot water, which of course is a smaller percent of the load in this building type than in a residential building. When we put all of the savings for all of the different prototypes across climate zones on a graph, you can see that the savings vary considerably by building type, with large office achieving the least savings in this set of measures, because our measures are focused on things that haven't really made it as strongly into code before, such as service hot water and some of the envelope measures that are less critical in an office than in a residential building. So you can see that we have significant savings in apartment and hotel, and also pretty significant savings in school. It varies by climate and office. You know, the savings are not inconsequential, but they're smaller than the other categories. But as with all analysis of code performance, this gets weighted across climate zones by population and building type. And when we put that all together, the average savings across the entire building sector is just over 20% for this analysis. So let me talk a little bit about what is in the documentation that we've put together. This is information that's available to you from our website. There's a whole bunch of supporting information, including this webinar will be available, but also the analysis from PNNL and a white paper about that analysis, etc. So let me talk about that for a minute. So on the left column of this slide, you can see all the different pieces of the 20% stretch code provisions that we've put together. There's an introduction policy brief document, a short document that you can use with policymakers. There's major descriptions, detailed requirements, etc. down the list. I'm going to go through these real quickly just so you understand what they are in more detail. So we have a standalone summary piece. This is meant to be an explanation of what stretch codes are and how they can be used. This is kind of a policymaker leave behind. So if you're working with a city policymakers or other political organizations that want to understand what we're working with here, this is a very short explanation of the stretch code. This is meant really just as a high-level summary. The main document looks like this, again, available on our website. And this is the whole package right here, all put together. It's also meant to be divided up if you want to target certain audiences with more or less technical information. So this is the cover of our 20% stretch code provisions. We have an introduction that goes into detail about stretch codes, how they are used, what they're used for, why they're a good idea, etc. Again, just an introduction to the concept of stretch codes. There are short descriptions. This is the short piece that goes through all of the measures that are in the stretch code. And I should point out that what I'm talking about now is the commercial side of this code. This goes through all the measures that we've defined to identify what strategies to use to add over your base code to achieve these savings. And it's a little hard to see in this, but the right-hand columns show the correlation with different sections of ASHRAE and IECC code to show you where this language would affect the existing base codes. So we did the analysis to ASHRAE 90.1 2013, but we also compared the code to IECC standards as well in terms of figuring out where it aligns and where it affects the code. There's a longer narrative about each individual measure through the course of the document. So this example here shows interior lighting controls requirements. You can see that we have a description, a purpose, and technical requirements for each measure going through the bundle of measures. And then there's a bunch of case studies in here of jurisdictions that have adopted stretch codes. And those are pretty good examples to share with policymakers who are considering this. If you're trying to make the case that a stretch code should be adopted, you can get an understanding of what the implications are at the jurisdiction level. Eventually, in order to adopt this as code language, you need to write the specific language that allows you to identify what is required in the code. This is highly variable depending on what your code baseline is, what your city policy is, and what your code cycle looks like. So in our document, we have identified the sections of code that would be affected by adopting these measures, and we've written the requirements, but we have not written it into code language, specific code language. We are happy to work with jurisdictions to adopt specific code language, but there are many different variants, and it would be a large effort for us to write it for every possible use. So instead, we are willing to work with you to help you identify exactly how to convert the language we've written into your local code. So let's talk for a minute about some of the commercial measures. I'm going to hand this off to Mark Lyles to talk about some of our specific measures, and then we'll come back to some more general information. Mark?
Great, thank you, Mark. I'm going to provide a quick overview or a snapshot of some of the commercial measures that you can find in the stretch code document. There are 22 measures in total, and I just plan to highlight a couple for you today. These are the ones that I'm going to provide a snapshot on. For each one, I will provide just an overview of what the requirements are that are in the document. A breakdown of the energy savings that we saw from that measure through the analysis done by PNNL, and then what I'm calling an illustrative example of how we're seeing that measure being played out in the field, either from research that we've done or other information that we've found from people who are really leading designers and engineers in the field. Whoop. So the first one that I want to talk about is air barrier performance. What we are proposing here in the stretch code is that for buildings that are under 50,000 square feet, they need to reduce air leakage through the thermal envelope by blower door testing their buildings. For buildings that are over 50,000 square feet, There's a couple different options that buildings can comply with. The first is to do either component testing, so either looking at a floor by floor basis, or they can participate in a continuous air barrier commissioning program that is conducted by a third party entity. As you can see from the analysis, the results are more significant in the cooler climates, which makes sense. And we're also seeing significant savings here from the multifamily prototype. For the example here, I want to highlight an ASHRAE research paper that is looking at 31 different buildings in Washington State. Washington State and the city of Seattle have had this as a code requirement since 2009. So they have a good baseline of how this has impacted commercial buildings kind of over a longer period of time. What this paper looked at was five different air barrier types. You can see them there on the right: liquid applied, curtain wall, window wall, sealed sheathing, and sheet applied. And it found that all but 4 buildings that they looked at met or exceeded the proposed air leakage targets. And the paper concludes that a qualified design team should have no problem achieving the 0.4 CFM per square foot air leakage requirement that we are proposing in the stretch code. The next one I want to highlight is thermal bridging. We're excited to introduce thermal bridging in the stretch code document because we know that under the current model codes, there's no good way for those codes to address thermal bridging through the thermal envelope. What we're proposing here as a requirement is that design teams need to account for thermal bridging by using an area weighted average for each envelope component. So instead of looking at the entire assembly, we're asking design teams to look at the different components, and in this case, when they have a surface area that exceeds greater than 1% of the area of that portion of the envelope that they're accounting for. So for the roof, the wall, etc. They don't need to do that if there's at least an R5 continuous insulation underneath it, which has been shown to reduce thermal bridging. But we're asking them to account for this for a majority of their common envelope interfaces. Because the code does not really have a good way of addressing this, you can see that there are significant energy savings from this measure, especially in the cooler climates. We only looked at this for the high-rise apartment and large hotel building prototypes, but we hope to be able to analyze this for other building prototypes going forward. Just a kind of quick introduction of what thermal bridging is for people who may not be familiar with it. Thermal bridging is caused by highly conductive elements that penetrate the thermal insulation and or misaligned planes of thermal insulation. They allow heat flow to bypass the insulation layer and serve to reduce the effectiveness of the insulation. In that picture there below, you can see that the shelf angle that is supporting the brick there bypasses the blue rigid insulation, basically compromising the value of that insulation, allowing heat to bypass that insulation. A lot of this information that I'm showing here is coming from a really great resource that is put together by Morrison Hershfield and available through BC Hydro, called the Building Envelope Thermal Bridging Guide. I've provided a link there at the bottom of the screen for people who want to take a closer look at this document. I'm also going to just quickly provide an example of how they're proposing to account for thermal bridging and some tools that they make available to design teams. In the example that I'm showing here, they're looking at the U value for each construction type found in a typical high-rise residential building unit. And you can see that they have called out the key components of that envelope here for the concrete wall and then the window wall spandrel. And they include in their document a catalog where they've modeled the energy flow or the heat flow through each of those typical details within the thermal envelope. I just wanted to highlight a couple things here. What I've circled here in red, they're showing the overall U value for the concrete wall and the overall U value for the window wall spandrel. So that is getting a little bit to what we're proposing through our area weighted analysis that we were proposing in the stretch code. I also want to just highlight the balcony slab here, which even though it accounts for a smaller portion of the overall envelope, is the second highest, is responsible for the second highest amount of heat flow through the thermal envelope. So we know that thermally broken balconies are a major source of heat loss from buildings, and we just want to make sure that design teams are accounting for it in their designs. The next one that I want to talk about is our efficient HVAC or dedicated outdoor air system measure. This measure is focused on either selecting high efficiency HVAC equipment, and then the values that we're providing in the stretch code document, they exceed the federal preemption values. So we are proposing this as an option. So you can either go with the high efficiency HVAC equipment, or you can do a dedicated outdoor air system. The modeling results that I'm showing on the right-hand side of the screen are just for the HVAC, the high efficiency HVAC equipment. And you can see that we're getting significant savings from the warmer climate zones where there's a higher need for cooling, and you're seeing that the efficiency of the cooling equipment is providing significant energy savings. The example that I'm showing here relates to a dedicated outdoor air system. And it's from a project that was done by Ecotope up in Issaquah, Washington. Ecotope has had a lot of success. They're a leading engineering firm, and they've really been pushing the envelope with dedicated outdoor air systems. What they've done here is they've compared a dedicated ground source heat pump with a dedicated outdoor air system to a ground source heat pump with a water to air heat pump, and a water source heat pump with a boiler system. You can see those are the three bars that are being displayed on the right-hand side of the screen. The ground source heat pump with the dedicated outdoor air system is the highest performing system with a modeled EUI of 33, which is a quarter of the energy of a typical regional fire station. And you can see that most of the savings that are being accounted for here are coming from that blue bar, which is fan energy that is needed for ventilation air. Service hot water heat recovery is the next measure I want to talk about, where we are proposing that project teams utilize heat recovery and or solar thermal water heating to meet at least 40% of the domestic hot water load. This has significant implications, energy savings implications for high-rise or multifamily building types where you have a higher hot water heating load. And this aligns with a lot of the analysis that we've seen done for our multifamily initiative that is also available through our website. The example that I just want to highlight here is a drain water heat recovery unit, which is one way to satisfy the requirements of this measure. And what this does is basically all that hot water that's going down the drain of your shower is being recovered by preheating that water before it goes into your hot water tank. We've seen this being applied in many Canadian provinces, where it is even a prescriptive code requirement in Manitoba and Ontario. And a lot of manufacturers for this technology are up in Canada. It is also being proposed for Title 24, 2019 through the CASE initiative. So we will be tracking that as well. but lots of opportunity here for energy savings. Interior lighting control requirements are really structured around requiring additional occupant sensor control in most spaces. So we're expanding upon the base requirements that are found in 90.1 2013 for additional spaces that need to have occupant sensor controls. The way that we've structured it, there are specific requirements for open office areas that are greater than 300 square feet. And then also for sleeping units, also need to have control devices that will automatically switch off all permanent luminaires and switch receptacles within 20 minutes of the space being vacated. So that applies to mostly just to hotels. The example here that I am showing is from our 2015 study on zero ZNE building controls. And in this study, we looked at 23 building control systems in 23 ZNE buildings. And when it came to the lighting systems in these buildings, we found that not only were they really efficient, they had really efficient LPDs, they were 40 to 60% less than code. A majority of these buildings were using photocells and occupancy sensors. And the controls, the lighting controls themselves were accounting for a significant portion of the whole building energy savings. In no cases was the energy savings less than 11%. So for these really high performing ZNE buildings that we looked at, the design teams were accounting on photo controls and occupancy sensor to deliver significant energy savings. And the last one I want to talk about is just a plug load reduction. As Mark mentioned in his introduction, this is something that is a big bugaboo for us, just because a lot of the plug load equipment and loads are really outside of what you typically find in energy codes. For the requirements, we are pulling in the requirements from ASHRAE 90.1 2013 about that 50% of all receptacles need to be controlled. So even though we couldn't claim any savings from that measure through the modeling analysis, we still wanted to make sure that that was in the code for any jurisdictions that might have the IECC as their base code, so that they have that as well, because the 50% controlled receptacles is not in the IECC model codes. We're also requiring the utilization of a power management program for all networked personal computers, as well as a specification of ENERGY STAR rated kitchen equipment. As you can see, the ENERGY STAR rated kitchen equipment is really driving a lot of the energy savings that I'm showing on the right-hand side of the screen. The example I just want to reference is coming to us from Seventh Wave, who's done a lot of great field research on plug loads. In this case, they went out and gathered baseline data from 8 office buildings in Minnesota, I believe, and they looked at the impact of different plug load reduction strategies, and they found that the computer power management saved the most energy compared to the additional strategies that they looked at. So it was just over 29% per workstation, just by enabling the ENERGY STAR recommended computer power management settings associated with that. So with that, I'm gonna pass it back over to Mark. That is just a snapshot of the measures in the 20% guide, and Mark's gonna take you through the residential requirements. Mark?
Thanks very much, Mark. So what we've been talking about so far is the commercial code requirements that we've built into our stretch code provisions. Residential requirements we treated a little bit differently. So I'll go through some things about that. Mark, you need to give me back the slides. There we go. So the first thing we did is look at leading residential developers around the country in different climate zones to see what they were doing to achieve high performance in residential requirements. So as many of you are, I'm sure, aware, in residential, there's a lot of use of the HERS rating system, the home energy rating system. and that has been adopted into IECC code as an ERI, an energy rating index for residential homes. And that is the way we've sort of queued our REACH code approach. In California, they have a slightly different term for a similar protocol. So first we looked at what's going on in different climate zones with leading home builders to achieve really low HERS scores, what's involved and what's incorporated. So we looked at case studies of all of these. And try and get the next slide going here. Sorry. So some of the features that are going into the best performing homes with the lowest HERS ratings are listed here, including extensive under slab insulation, really good wall insulation, really good roof insulation. Home automation systems play into this as a feature. Whether they are directly contributing to energy use or not, they provide the potential for better integration with energy systems. Ground source heat pump is a common feature, or a relatively common feature in high efficiency homes. Energy recovery ventilation and heat recovery ventilation we see very often, and some other features like gray water storage and recycling, which doesn't directly contribute to energy use per se, but it's part of the package of these leading edge homes that we see. Of course, the windows are very good. We often see low E house wrap, very good airtight ceiling, excuse me, and occasionally PV and battery storage. So these, again, you can see that these are features. Some of these are energy features, and some of these are related sustainability features, but they're fairly common in what's considered sort of the best homes being built out there now. So based on this, we looked at HERS scores of different code prototypes, and that's what's shown on this chart here. So on the left, the code or program is identified. The approximate HERS ranking or ERI ranking is shown in the second column. Some envelope requirements in the third column, and other features in the right column. And our 20% REACH code strategy is the yellow highlighted row. So we're targeting an ERI of 46 to 50, which is better than current IECC requirements, not quite as good as the passive house standards or the ZE Ready home that has been released, but pretty close. We're following the IECC enclosure plus 20% for the requirements, and then we're adding heat recovery, the EPA indoor air package. Ducts are required to be in a conditioned space, and it needs to be at least solar ready. So that gives you an idea of where our residential REACH code strategy falls in the larger environment of HERS ratings. You can also see the third row down is Energy Star 3.1. So we're targeting a performance a little bit better than that, and IECC is also moving ahead of that now. So hopefully Energy Star will move up in that. So that gives you an idea where we're at on our residential code targets, and that information is going to be on our website soon. It's not there yet. Right now we've released the commercial package, but we can give you the targets for HERS, which is sort of a self-contained system, which is great. It's a great way to work on thinking about advanced performance in residential sector. So let's talk a little bit about where we want to go from here with our REACH code development. NBI is involved in developing code strategies and REACH code programs and so on all around the country with different jurisdictions. Within the context of this model stretch code strategies, we are still planning to release a 40% strategy, a design standard. Much of it may be adoptable as code, but some of it is probably going to require other policy approaches. And we're working on Z&E code performance standards. And all these things are happening simultaneously. We're already working with jurisdictions that are targeting higher performance than 20% above 2013. We've also worked with a few jurisdictions that are piloting Z&E code approaches or thinking about how they're going to adopt those, or looking at outcome-based performance approaches. So there's a lot going on in the code world with different jurisdictions experimenting with different approaches to aggressive performance in the building sector. We've sort of talked a few times about unregulated loads. I wanted to show you this graphic, which gives a really good explanation of sort of what we're up against in terms of building energy use regulation. So what you see here on the left are the names of the different building types represented by these bars. The horizontal bars are split by a vertical black dotted line, Everything to the right of that line is regulated end use, and everything to the left of that line is unregulated end use. The gray bar at the very left edge of each of these is what we call bad operation, and that represents problems of schedule conflicts or control issues or whatever. Even though we design buildings to work perfectly, none of them actually do. And so when you submit a code submittal for a building, you're assuming that everything's going to work the way it's supposed to, and that's what the code wants. But of course, we know that doesn't quite happen. So we try to account for some of that. And of course, that's an unregulated load because there's no way the code can address that directly. But the main point here is to look at what percentage of total building energy use is regulated versus unregulated. So at the bottom of this, the very lowest bar is small box retail. And in that building type, just over 20% of end use is unregulated. At the top is restaurant. And in that building type, more than 60% of building load is already unregulated. And this is with a current code. This happens to be the Washington State Code from a few years ago, an analysis of that done by Mike Kennedy. But what we see is that a large percentage of our loads are already outside the scope of code. And so we have a difficult time regulating them. And that's going to become more and more the case. So that's why I talk about needing to think about other policy approaches to unregulated loads to get to the kinds of net zero and 50% reduction or 80% reduction targets that have been set around the country. So when you take the end use breakdown from the last graph and multiply it by the building population, so in the case of restaurant, 60% of their load is unregulated. In the case of office, it's more like 40. But if you multiply that through together across the entire building sector and think about the end use breakdown, this is a weighted end use energy breakdown across building types. So across all building types, up on the upper left here, you see that 30% of building energy use is unregulated equipment. And in the lower left quadrant, the orange pie is heating equipment across building types. 23% is heating, and this is a colder climate weighting, I should point out, because the cooling energy is a little higher when you look at the whole national average. So in this case, though, the first two loads, the biggest three loads, if you include the orange other equipment, elevators and things like that, that are pretty much outside the scope of code. 2/3 of the energy use of buildings is difficult to regulate. Heating is difficult to regulate because equipment efficiency is federally preempted. Of course, you can reduce heating energy use by improving the building envelope, but in general, you can't directly tackle these through the code cycle the way codes are written now. So we need to think about strategically to get to the kind of performance we're talking about. We need to strategically think about mechanisms to start addressing these unregulated and difficult to regulate codes. So when we talk about a net zero code, for example, this is what a code progression kind of looks like. This is a graph for using an example of Washington State, which has set a goal of reduction by of 70% for energy use by 2030 from 2006. And what you see is if the blue part of this bar is regulated energy use, and the orange is regulated energy use and the blue is unregulated, we can squeeze down the regulated energy use quite a bit, but we can't get rid of it completely unless we suspend the laws of physics. And for unregulated loads, we have less ability to tackle those. So to get to net zero, we basically have to offset the energy used by the building in PV contribution. So I think we're going to see in codes more and more requirements to offset energy use with renewables, whether that's on site or some other mechanism. But you can see that we're not talking about buildings not using energy, which is impossible. We're talking about using less and less energy so that we can offset it with renewables. So this is the way to think about code progression. So a few other resources I want to mention that we have for codes, and there's a lot more resources than this, but I want to highlight these. One is that we've recently published a paper, Mark Lyles, who's on this webinar, and Jim Edelson from NBI, our Director of Codes and Policy, published a paper on federal preemption. It's a discussion of the role of federal preemption in code development. It's a great paper. There's a lot of interesting issues in there that sort of talk about how difficult it is to regulate heating energy with federal preemption in place and what we might try to do to work with that. Another document recently published that we worked with the National Institute of Building Sciences on is the implementation of an outcome-based compliance path and energy codes. This is guidance for cities who want to target an outcome-based performance path in energy codes, that is regulating on actual energy use instead of on building physical characteristics. This is based on a pathway that was proposed and adopted by IGCC, by us and NIBS a few years ago. It evolved since then, and we've done a lot of work thinking about what the policy looks like at the city level. So this is also an interesting read if you're looking in that area. So with that, I'd like to open it up to questions. Mark Lyles is going to manage the question process. Thank you very much for joining us, and please stick around to hear your questions asked and answered.
Great, thanks, Mark. The first question that came in here is someone was curious about the timeline for the 40% and Z&E stretch code. Mark, do you want to speak to that one?
Sure. So the 40% we're working on right now, we're hoping to have that out around second quarter of this year. Again, as I mentioned, it's going to be sort of design guidance, and we have a lot of great information already on multifamily from a guide we published and the information here. So there's more coming, probably second quarter this year. As far as the net zero code, the document I just showed you that was published with NIBS, which is an outcome-based code, which is, you know, regulating on actual performance. That's sort of a good model of a net zero code. A couple jurisdictions around the country have adopted strategies for that, including Seattle, and I think DC is in the process of that, and San Francisco is considering it as well. I would also point out that if you achieve a 40% savings below ASHRAE 90.1 2013, you're pretty much in striking distance of what we see at NBI for net zero buildings, you know, if you put in renewables. So getting somewhere, you know, the net zero code is not another 40% below the 40% code. Once you get to that level, for certain building types, you're right in striking distance for net zero. So sorry, that's kind of a roundabout answer, but.
Great. The next one, someone was curious about what our ZEPI score is for 90.1 2016. Mark, do you?
Yeah, I can skip up to that. Actually, we base, for the model, the national model codes, we base that on determination analysis by PNNL or DOE contractor to determine that. I don't think that's been released officially yet. I will tell you that it's somewhere around very low 50s, maybe 50 itself. But that is, for now, it's an estimate.
Right, because yeah, that
hasn't been released yet. Could be 48, but it's going to be right around there.
The next one was just someone was curious about what the different colors in this map represented, because there doesn't seem to be.
Oh, I'm sorry. I pulled that off the BCAP website, which is a great resource. There's all kinds of information there. The darker the state, the more recent code they've adopted in terms of versions of ASHRAE or IECC.
And then someone was curious about how water management lowers HERS scores. And I guess the answer to that question is that I don't think that the water management is calculated into the HERS scores. I think that we were just mentioning that in our example as just highlighting some of the features that we found in buildings with lower HERS scores. So builders that are building residences that have low HERS scores are also including water management strategies. Would you say that's correct, Mark?
I don't know the answer to that, and I'm not sure you're right as to whether the water is not in HERS. I think it might be, but I don't know. So let's leave it at we don't know the answer to that question rather than wrong information. But Mark is right that the examples we showed are the features that we see in low HERS scores buildings, whether they contribute directly to those scores or not.
Someone wants to know if you can summarize a few of the strategies for heating load reduction.
Sure, and interestingly, I think one of the most compelling strategies being talked about in the market now for heating load reduction is the passive house. And passive house, for example, in Vancouver, BC, they've adopted a zoning requirement for upzoning based on what they call TEDI, thermal energy demand intensity. And they give you an allowance for total heating energy to heat your building in that case. And in order to achieve that, you need to make sure you have a really good envelope with low air leakage and heat recovery to reduce the heating load enough to reduce the heating energy substantially. And they actually regulate how much you can put in. Passive House, the program it's based on the Passive House requirements, which require really good insulation, really tight envelope, really good windows, heat recovery, all focused on reducing total energy use, heating energy use. And so even if we can't regulate equipment efficiency, we can reduce heating demand with a really good attention to the building envelope. And we've incorporated a bunch of features of Passive House requirements into this stretch code, including attention to thermal bridging, envelope insulation requirements, envelope sealing requirements, encouraging a dedicated outside air system separated from primary heating and cooling. All those come right out of strategies to achieve Passive House.
Great, and then it looks like someone was just stating that they thought that the preliminary determination for 2016 IECC or 90.1 2016 saved about 7% compared to 90.1 2013.
So 7, that puts it right in the score that I mentioned. The 2013 ZEPI score is about 54, so a 7% reduction from there is right around 50. So.
Someone wants to know when the residential 20% stretch code report is going to be available. And also, are ERI and HERS scores interchangeable?
So ERI and HERS scores are, I want to use the word carefully. HERS is a private system developed by, I believe, ResNet, and it's implemented by third-party reviewers to score a home on the HERS scale. Because the IECC process is an ANSI process, they have to use a consensus-based development of a standard, and so they can't use a privately implemented standard like HERS, so they've adopted ERI instead. I think there might be some very subtle differences, but essentially it's the same approach. And the 20% stretch package, other than the targets, information about the prototypes and strategies should be available in, I don't know, probably about a month. Maybe sooner.
Okay, it looks like that covers it for questions and comments.
I'll just point out that this video of this webinar will be available on our website soon for sharing and review. Thank you so much for joining us, and please send us any questions you have and peruse our website, because this information is there and there's a lot of great stuff there about code strategies and advanced construction strategies and zero net energy and a whole bunch of other things. It's a great resource. Thank you so much.